Thanks for the invitation to this nice place. It's always a pleasure to be back in Marseille, especially at CERN. Today I'm going to talk about geometric quantization of toric and semitoric systems, taking as the viewpoint, which is quite residual in the theory, of real polarizations. Okay? At the end of my talk, I will present a quantization of K3, and I will compare the result using these tools of real geometric quantization, and I will compare these to the Keller quantization point of view. The nice thing about this point of view is that it connects very well to the theory of singularities of integrable systems, so it has also some interest from integrable systems point of view. So what I'm going to present, these are very old pictures when we were all young. This is joint work that started a long time ago with a student of Yale Karshon, Mark Hamilton. Then I will also, we started, Mark Hamilton did the thesis on the toric case, and then we started to consider other kind of singularities with Mark, which were the hyperbolic singularities. And then with Fran Presas, who has a big culture of algebraic geometry, we tried to develop tools to attack the problem of general Lagrangian foliations. And with my student Romero Soya, we did the case of semitoric systems. So this is a little bit joint work with these three people. And it's contained in several papers, essentially 3 papers. 2 of them are published. The semitoric one is still not published. So, well, this is my starting point, the classical picture, our dream of geometric quantization to build a bridge between classical and quantum systems, okay? And essentially, there are many ways to go to the other side. We saw one way before. We will see many ways in this conference, and the idea is to see how they are related. Maybe there is no best answer, but understand why a given representation as a Hilbert space is good or bad. It's already a good conclusion for us. So this is my point of view. The idea is that we want to build a Hilbert space and to define a way to quantize also the bracket. For the kind of geometric quantization I'm considering today, the real polarization, in this picture it's quite disappointing because I will just give the Hilbert space and I will not define the associated commutator. So this is the starting point. I'm going to consider a symplectic manifold. Today I'm not going to consider Poisson manifolds. I'm going to be symplectic. I'm going to consider a symplectic manifold with a symplectic form defining an integral class. And automatically, because the class is integral, I have associated to it a line bundle. So I take a complex line bundle with a compatible connection such that this curvature satisfies this equation here. Ooh. What happens? Well, this is the pointer. Well, okay, the pointer is not working. I will use the hand. What? A little star up? Ah, good to know. Thanks. Okay. No, I don't know how I did. I did a disaster. Okay, thanks. So here, that's the equation satisfied by the curvature. And what is a real polarization? A real polarization is just a Lagrangian foliation. Okay? Give me examples of Lagrangian foliation. So a wide class of examples of Lagrangian foliation and symplectic manifold comes from considering an integrable system on my symplectic manifold, which I'm going to look at as a map on Rn, where its components satisfy some commutation conditions. And I assume, of course, that they are generically independent. If the manifold is compact, there's no way I'm going to escape the singularities, okay? There will be some singular points, and I am a person especially interested in singularities, so I will look at those singular points. So first I will describe what happens with the regular points. What happens with the singular points? At the singular point, what is the foliation, by the way? The foliation, I can look at the foliation in two different points in two different ways. One is I look at this as a fibration, and I consider a foliation whose leaf at a point C is given by F1 minus C. I could also look at this foliation in a different way. I could also look at a different foliation, and sometimes they are the same, defined by the span of the Hamiltonian vector fields. And because of the commutativity rule, okay, because this commutes, automatically I get that the brackets are 0. So this is really an integrable distribution, and it defines a foliation. With some conditions on F, okay, these foliations are the same. In particular, if I consider a regular compact fiber, they are the same in a neighborhood, okay? So I want to look at integrable system as a general class. Of course, not every Lagrangian foliation is an integrable system. So it's also good if I compute the geometric quantization of an integrable system, it's also good to see if I have tools to compute the general case, right? Because an integrable system is very restrictive. I have a fibration, and in the general case, in the general Lagrangian case, I may have very strange behaviors, okay? So when I talk about flat sections equation, I did the same error. With respect to this connection, I mean the solution to this equation, sections of the line bundle, okay, and the solution to this equation. Here, okay, there is a moment in which you need to define if you go for the metaplectic correction or you don't. We could consider the metaplectic correction at this point, or we could not consider it, and then compare the results. They are isomorphic. So when I consider the flat sections, you can think that you have or you don't have this metaplectic correction, as you prefer. Okay. So what is a Bohr-Sommerfeld leaf? A Bohr-Sommerfeld leaf is a leaf of this polarization admitting global flat section. So I'm going to take this simple example. I take the cotangent bundle of S1 with this form, with this symplectic form, and with this polarization, okay? And I consider the trivial line bundle with this associated connection. The equation of the connection is given by this formula. So flat sections satisfy that this is equal to 0. So in this case, it's easy to solve the equation that this is equal to 0. And flat sections are given by sections of this type. Okay? So if I want, the polarization here is described in these terms. Here we have an example in which I can look at it as the fibers of T, or I can look at it as the span of partial of theta. This would be this, in this particular example, these two foliations. Okay, in this case they coincide, okay? And in this case, to have a globally defined Bohr-Sommerfeld leaves, I need to have this T, because I'm going to go around S1, I need to have an integer here, okay? So I only have a discrete number of Bohr-Sommerfeld leaves, which are defined by the condition that T is an integer, okay? So if I consider an integrable system, and I consider a regular leaf, then this example is canonical in a way that in general I'm going to have the same situation in higher order, a similar computation, and what do I get then in the general case is a theorem by Gillen and Stenberg, which tells me that if the polarization is a regular fibration, this is, in a way I can think that semi-locally this is equivalent to having a regular integrable system. Then I have a regular fibration with compact fibers over a simply connected base, okay? Then in this case, the Bohr-Sommerfeld set is just given by the points, okay, by the integer points, integer values of the map defined by the global action coordinates. In a way, if I consider an integrable system, it's defined by the integral values of F1, Fn. Okay? Whenever I have already taken action coordinates, if I already assume that F1 and Fn are action coordinates. Liouville-Arnold Mineur theorem guarantees that this is always the case in a neighborhood of a compact set. Okay. So for toric manifolds, of course, I can think of the base as the image of the moment map, and the whole theory now connects back to Delzant polytopes. So it's a good moment to remind what is Delzant theorem. Delzant theorem gives a one-to-one correspondence between toric manifolds and the image of the moment map and the Delzant polytopes. And Delzant polytopes are the image of the moment map, okay? So there is a whole theory behind this. We know that toric manifolds is a particular case of a manifold endowed with a torus action, so the image is convex by the theorem of Atiyah, Gilliam, and Stenberg, but we know more. In the case in which the toric manifolds case is the case in which the rank of the torus that acts on your symplectic manifold has half the dimension of the manifold, and you assume that the action is Hamiltonian and effective. Okay, then you consider the moment map, and you look at the image of the moment map. Here we have an example, the two-dimensional example. I take the symplectic sphere, okay, and I consider the torus action is a toric action, which I consider it's just a circle action, which is rotations on the sphere. This is, this is what happens every day on the Earth. We are rotating, and the moment map in this case is just the height function, okay? So the height function, of course, the image is just an interval. And the nice thing is that, well, over this interval, I can look at the pre-image of the moment map, and this defines here the foliation of the sphere by S1s, which is a Lagrangian foliation. It's a particular case. So all the Delzant polytopes give me hundreds of examples of real polarizations. Okay, because this is a particular case of an integrable system. This is a beautiful integrable system. And another example in CP2, which I couldn't draw because it's in dimension 4, but I can draw the image. Okay, I consider CP2, and here is the action which I consider is a torus action, and the image is just this triangle. So Delzant theorem tells me that the image is not only a complex set, but it's a nice polytopes where there are some conditions satisfied by the slopes. Okay, there is a whole group of people who have been working on toric manifolds, doing things on these polytopes, like cutting here this side and see what happens on the initial manifold. I will go back to this initial point, to this idea at the end of my talk to quantize K3. Indeed, I will use this chop of the sides, which is a symplectic cutting. Okay, so now I want to quantize the case of fibrations, and where we are is that a way to quantize would be to count the Bohr-Sommerfeld leaves. We saw, because of this theorem of Gilliam and Stenberg, which comes from working out the computation via the Arnold-Liouville theorem, tells me that there is a discrete number of Bohr-Sommerfeld leaves. So a way to quantize, a first proposal is, why don't you count the number of Bohr-Sommerfeld leaves? Okay, this could be a proposal, okay? And what is this meaning of counting? This is what I want to say, to clarify now. How can you identify this quantization with counting the Bohr-Sommerfeld leaves, okay? So there is a theorem by Sniatyski which tells me that this is the case, that you can always quantize by counting the number of Bohr-Sommerfeld leaves. But how do you do this? How did he define? Well, in which cases? Of course, Sniatyski did this in a miracle case, in the case in which the leaf space of your Lagrangian foliation is a Hausdorff manifold. Okay? So you assume that it's Hausdorff, and you assume that you are in the case in which your Lagrangian foliation is given by a fibration, okay, with compact fibers. Then he proved that the quantization is given by the count of Bohr-Sommerfeld leaves. But did he define the quantization as such, or did he compute it in some particular way? He took as a starting point an idea by Kostant, which is the following. In case there are no global sections, which we saw in the example, it's very hard to have global sections, then you define your quantization as the...
I don't think he insisted on contour-keeps. I think he had different cohomologies in different cases.
Yes, well, you have also the cylinder case.
His theorem is actually stronger than...
Yeah, well, you have the cylinder case, but you have some other conditions that, okay, for the use I'm gonna make, it's okay. Okay, so we define the quantization as the sheaf cohomology, okay, over the sheaf of flat sections of this line bundle, okay? This is our definition of quantization. It's just sheaf cohomology. So that's good, because if we like algebraic topology, we just need to compute the sheaf cohomology and then interpret the result in terms of geometric quantization. So this is what Ziatinski did, okay? And he proved, in the case in which it's compact, in the case in which the leaf is compact, that this quantization indeed leaves out of all these cohomology groups, you can discard all of them except half of the dimension of the manifold. So all the cohomology is localized on the degree n, okay? And the dimension of this is just the number of Bohr-Sommerfeld leaves. So this gives this interpretation of, okay, let's just count Bohr-Sommerfeld leaves. Let's talk a little bit about sheaf cohomology. Why not? It's a good moment of the day. It's 10:25. It's the moment to talk about sheaf cohomology. And okay, the starting point I'm going to take is the point of view of foliated cohomology. Okay, in foliated cohomology, you have this complex here. Okay, here I consider, instead of the sheaf of real valued, I consider complex valued functions, because I'm going to need this, because I'm going to consider then sections of the line bundle. But initially I have a foliation. I just can consider the complex of foliated cohomology, okay, in which I just consider sections of this bundle. So I can compute sheaf cohomology from the RAM cohomology, just projecting on the tangent. I just take the RAM differential, and I project I do the differential on the ambient space, and I project down to the polarization. And this works well. So one way to go would be, one idea would be, okay, this is a nice fine resolution of the sheaf of complex valued functions. So let's just twist this with the sheaf of flat sections, and let's see what you get. And that's the idea. The idea is that we just twist this resolution with this sheaf, okay? In the case in which the polarization is regular, it's very easy to check that this is a fine resolution. In the case in which the polarization is singular, it's not necessarily true, okay? So one of the things you need to do is, if you have some singularity, to prove some kind of Poincare lemma, and then that's the general idea. Okay, so the idea is we are going to take as a starting point foliated cohomology, and we're going to twist to compute the cohomology, which I'm going to call the Kostant complex, which is just the sheaf cohomology, okay, where the sheaf I consider is the sheaf of flat sections of the bundle. Here I put that the bundle, if you look at my paper, sometimes, you know, I consider just this line bundle, and sometimes I do the metaplectic correction. It's isomorphic, the results, if you do the metaplectic corrections or you don't. So I'm putting this in brackets because you can take the point of view which you prefer. Okay, so let me talk about the general case of Lagrangian foliations. Well, because this fine resolution approach, this is something we started to work with Romero Soya in his thesis, but indeed the general Lagrangian case we did with Fran Presas, okay? And then one thing you can try to do is, okay, of course the first goal would be quantize all possible real polarizations. But okay, this is quite such a big dream that it's too big, right? But in dimension 2, because Lagrangian foliations is just given by a line field, maybe it makes sense. And for instance, there is a classification of line fields by Denjoy and Nesser and Schwarz. This is a theorem where you have a classification that tells you that you have either some periodic orbits, and then you have some places in which you have these kind of Reb components. So essentially, if you have the right tools and you can just chop your manifold and understand each of the areas, maybe there is a hope to compute the sheaf cohomology. Okay, this is calling us. Wow, I went too quick here. Okay, if I want to understand, let's see, the sheaf cohomology by cutting pieces, of course I'm going to try to develop some computation kit, which will include Mayer-Vietoris and Kunet formula for this kind of sheaf. This is what we did with Fran Presas. And as an example, just as an example, if I consider the torus and I consider the irrational flow on the torus, so my foliation is just given by the rational flow, okay, I can compute this geometric quantization. And well, the first thing, one interesting thing of this viewpoint is that you can look at foliated cohomology as a limit case of geometric quantization. You may say, well, but you are doing in the presentation here, you had the other point of view. You started with sheaf cohomology associated to foliated cohomology, and then you just twist. Yeah, but in practice, sometimes it's better, I mean, you have a better understanding of this complex, and then you can rescue the foliated cohomology complex as a limit when omega equals 0. So you can always think as foliated cohomology as the sheaf of the Kostant complex when the symplectic form is 0. And this is what we did here, because essentially we computed this Kostant complex, and the conclusion is that so if you don't have a nice fibration and you have irrational flows, for instance, on the torus, so this is the first example you would say, okay, give me an example of a bit complicated. You ask for a student second year, he will give you, or she will give you, the irrational flow on the torus, okay? So if you compute it, you get an infinite dimensional manifold.
So you say question, what's the notation? So what is this J?
Which J? This is the sheaf of flat sections of the line bundle. Okay? So, well, it's a notation. This is just a quantization. I don't know if I put the G here. So in this notation, let me go back here. Maybe I went too quick. This is you are computing the cohomology of the sheaf. Okay, and J is the sheaf of flat sections of the line bundle.
Sections are flat
along, yeah, in the directions, in the polarizations. Okay, when I say flat sections, oh my God, I'm going back to my first slide. That's terrible. So notation, flat sections equation, it means that this equation is satisfied. Flat, it means that this equation is satisfied for all the directions tangent to the polarization that you have fixed. So I assume I have the line bundle fixed. I assume I have my polarization fixed. And with this data, I can define this Kostant complex, and I define the quantization as this sheaf cohomology, okay? So yeah, the notation, it's possible that I change the notation here. Here I put the quantization and I didn't put the J, but there is a J behind. Maybe I could just simplify my notation, sorry. So the quantization is always infinite dimensional, but if I look at the limit case when omega equals to 0, and I recover the foliated cohomology, then what I get is I get a finite answer if the rationality measure of this integral, this irrational slope is finite, okay? So I get a finite solution out of this infinite solution in the limit case when I have the rationality measure of eta finite.
In which cohomology does this live?
This lives, okay, that's a good question. You get one in H1, in H0, and you get one of the C's in H1. Yeah. Yeah. So all the details are in our paper. You get some interesting behavior.
What is the rationality measure?
The rationality, so this is what, I mean, if the number is a Liouville number, then it's infinite. Okay, then it means that if I have an irrational number, then for all n, I can solve the, so the irrationality, it's this exponent. Maybe I can write here. It's okay. Yeah, it's in the archive. It's even published. It's a long time ago. I was young then. Yeah, it's a Diophantine condition of this type. So essentially, you have something like this. And when this is infinite, then you say that it's a Liouville number. Okay? So when it's infinite, then your number here, I call it eta. Eta would be a Liouville number. In the Liouville number case, you always get infinite quantization. But if it's finite, even if the quantization is infinite dimensional, the sheaf cohomology, defining the foliated cohomology, is finite. So this improves a former result of Al-Kacchini for foliated cohomology. So this is sort of interesting from a point of view of foliated cohomology. Sometimes you make your life more difficult and you understand easier things. Okay, so what are the main tools? Well, the main tools is just to take the book of Bott and Tu and work a little bit hard to get a Q-net formula, for which you need, of course, some conditions. Otherwise, you'll need to, in general, of course, we know from Grothendieck that the Q-net formula needs a completion. But if you have something which I call mild conditions, which is that M1 admits a good cover and M2 is compact, for instance, then in this case, we have a honest Q-net formula here without completion, okay? And we also have a Meyer-Vietoris. So the idea is that you can compute this sheaf cohomology, the foliated cohomology and the geometric quantization cohomology, just by piecing out your manifold, because you have this Meyer-Vietoris, and if your manifold is a product, then you can use a Q-net formula. This point of view is nice to give a new proof, for instance, of Sniatycki theorem, which I'm going to do in the next slide. So just as an example of application, we can prove a we can give a different proof of a Sniatycki theorem using this computation kit that we did with Fran, because, well, it's enough to understand, essentially, the product. You are in the case in which you consider this foliation a cotangent bundle of Tn. So you have Tn times intervals. So you place yourself in understanding S1 times intervals. S1 times an interval, okay? So you need to understand with the foliation given by S1s, okay? Which is a little bit the example I did by hand, the computation of flat sections, okay? So now, and then what you do if you have an S1 is that you take two coverings of the S1. Well, you start with the case of the rectangle. You start with the case in which your manifold is just a product of intervals, and you have this symplectic form, and the foliation is this one, okay? Now you want to compute H0. H0 is the set of flat sections, but we computed the set of flat sections. We did this computation before. If I go to slide, this is going to be terrible, I'm going back to slides instead of fourth. If I go to this computation here, we understood that the set of flat sections in this case is given by this formula. So it's encoded in a function that depends on one of the variables. Okay, so this means that when I compute the triangle, the square case, I get these C-infinity functions on E1 with values in C. Okay, and then for H1 I get 0. Okay. For H1 I get 0, why? Because I'm in the regular case, and I can prove a Poincaré lemma, so H0 is equal to H1 is equal to 0 in this case. Computation 2, now I understand the product of an interval with an S1, and I'm going to need computation 1 to understand this one, because I piece out, this is a product of, this is S1 direction, and this is the interval, Okay, what I do is to take a covering, okay, of the S1 with two open sets, and I look at the intersection. Omega 1 and omega 2 are going to be the intersection, so this goes back to itself. So of course, I'm going to apply Meyer-Vietoris here. So this is just an example that one can do these computations by hand if one has the patience. In this case, I look, therefore, at this product as this union of two U and B, okay? And the intersection is the disjoint union of omega 1 and omega 2. So I plug my Meyer-Vietoris sequence, and I get this thing because this is the intersection, okay? And I jump from H0 of the total space to H0 of the intersection, of the sum of U and B, to the X0 of the intersection, which has two connected components. This is why I have a direct sum here. And this mapping here is the difference of restriction, as it's a standard in the Meyer-Vietoris sequence. So this is just a computation that I could give to one of my students, for instance, to Anastasia, who is sitting there. And, well, you have the patience to compute you want to understand what is H1, okay? That's the goal. So you do a computation by understanding this mapping here, and you write down, where here essentially you are just using, in these expressions, you are using that the parallel transport of the connection, okay? So you get this part here, and now you want to understand what is the dimension of this guy here. So, because this is a surjective map, everything amounts to understanding when the determinant is equal to 0 or not. If I take a Bohr-Sommerfeld leaves, then it will happen that the determinant is going to be 0. Otherwise, it will be different from 0. So this means that the codimension is 1 or 0. So H1 is 0 if there are no Bohr-Sommerfeld leaves, and it's if there is one Bohr-Sommerfeld leaves. So I can essentially just fish Bohr-Sommerfeld leaves by looking at a Meyer-Vietoris argument. This is not very interesting, but it's just to show you that you can prove, for instance, this gives a shorter proof of Sniatycki theorem by these second-year arguments. Okay, so if I want to consider the general case of the cotangent bundle of torus, well, I will just apply Kunev formula. So Kunev tells me that I just restrict to the lower dimensional case, and I make a product. So the final answer gives me a new proof of Sniatycki theorem, okay? Which tells me that Sniatycki theorem is going to tell me that first, this sheaf cohomology is localized as half of the dimension of the manifold, and secondly, that you are fishing, you have the total number of Bohr-Sommerfeld leaves. So it's really algebraic topology, what we are doing. So now, okay, with Fran, we enjoyed a lot looking this kind of computation tools, and so we have a paper where we do essentially the general Lagrangian case. Of course, because general Lagrangian foliations are still not well understood, we just give some examples. We don't do a total classification. We can do the two-dimensional case. Okay, so what about, now I'm going to go out of the box of general Lagrangian foliations, and I want to apply these tools to understand foliations that are simpler because they are given by integrable systems, but which may have singularities. So I want to understand if the singularities show up in this classification, okay? I want to understand also if these singularities of this integrable system have some well understood invariant, if this invariant can be read off in this sheaf cohomology. So let me start with a very simple example, the example of the sphere. In this case, of course, there are two fixed points, and fixed points correspond to singularities. So what if I try to include the computation of these 2 points? So more generally, what if I try to quantize toric manifolds? Who did this is Mark Hamilton, who did this in his thesis, and he gave the following answer. It's something, okay. What he did is to prove that the quantization is localized, of course, in half of the dimension, and that you don't see, so essentially he proved that you count the Bohr-Sommerfeld leaves, the regular ones, so if this is the image polytope, you just see the regular ones, and the ones which are on the boundary, which would correspond to singularities. So in this toric language, the points, the vertices that are on the edges or on the vertices correspond to singular points of your integrable system. Okay, so he computed all the sheaf cohomology at these points. He did it using check cohomology arguments, and the final conclusion is that they don't count. So when you do this sheaf cohomology, you only see the integral points which are inside. He did this computation without this metaplectic correction. But if you do the metaplectic correction, it's the same. You never catch the points in the boundary. Okay? So, well, that's interesting because, well, I don't know. It tells you that what you had in the regular case extends to the toric case. So at this point, what happens if you consider other singularities that are not the singularities that would correspond to vertices and edges of a toric manifold? So, because at these singularities, of course, you have Marl-Guillemin-Sternberg that tells you what is the normal form of your first integrals at this point, and you have an expression which is quadratic. And more generally, well, this is a theorem that Eliasson proves already back in his thesis, and this is a theorem that has many proofs. Because, well, myself, when I was doing the thesis, I provided a complete proof because the proof in Eliasson's thesis was complete in the completely elliptic case, but it had some cases that needed to be checked. So in my thesis, I gave a new proof of the hyperbolic case. And Sam Bunok there, he considered the focus-focus case. So if you look in the literature, you will find many, many proofs. So many people have contributed to this theory. Okay? So the theorem of Eliasson tells me that if you consider singularities which are called non-degenerate, then you have some kind of Marl-Guillemin-Sternberg normal form for these singularities. Okay? So you have a normal form for the symplectic structure and for the first integrals. So there is a hope to make computations. The symplectic normal form looks like this. So essentially the local model is the following one. You have your manifold is going to be the cotangent bundle. You can think of this as the cotangent bundle of Tk plus a disk. So you're going to have some components which are going to be regular, which is like the example I was discussing before, that I was even computing. And then you're going to have some singular components, okay? And among the singular components, you have some elliptic components, some hyperbolic components, and some components that come in pairs that are the focus-focus components. And this singularity is called focus-focus or foyer-foyer in French. And, well, it corresponds to a singularity where the fiber, at this point, you have a pinch. You may have several, you could have several pinches. And it's been, so you could have situation in which you have more than one pinch. And around this pinch, of course, this is a very, if you think of this in 3 dimensions, you are wrong. You need to think on this in 4 dimensions because you have like 2 planes that cut in a point. That's the situation. So this is a 3-dimensional picture. So essentially, if you want to do sheaf cohomology for this 4-dimensional gadget, you need courage. So this is what I will explain, because this is something it took us a long time to try to do this computation, but we did it. Okay. So we are going to hear about semitoric manifolds in this conference again, I think on Wednesday in the talk of Sue Tolman. So what is a semitoric integrable system? Toric means that the components are going to be either regular or elliptic, and semitoric, it means that we just exclude hyperbolic singularities. Well, essentially, you also need to assume that you have certain properties of properness and so on. But essentially, in terms of local model, I'm going to assume that I'm going to consider a singularity where I don't have these hyperbolic singularities. Okay? So, because the hyperbolic case is not in the semitoric box, I want to look at a computation, 2-dimensional computation we did with Mark Hamilton a long time ago. It was in 2008. We were all young. And, well, in the hyperbolic case, what we do in order to compute sheaf cohomology is to piece out the space we do a check homology computation. So this is we have to take a good cover of the singularity. This is the kind of singularity you have when you get one of these hyperbolic. So now imagine that you take an hyperbolic point. This means that at the point you have stable and unstable manifolds going out. And if you want things to be compact, you're going to have these 8 figures everywhere. Okay? So you'd better be able to compute the cohomology of these 8 figures. So what we did with Mark, I forgot to put, this is a theorem, well, this is a local computation that we did with Mark Hamilton, is that, well, the key point is to understand what is the sheaf of flat sections. And the leaf-wise flat sections are given by this equation, where A is a function which is flat. When I say flat, I mean flat in the sense of analysis, that all the partial derivatives at the 0 are going to vanish. I'm not in the analytic setting, so there are functions that satisfy this condition and are not 0. I'm in the smooth setting, okay? So the solutions, I mean, and this is a smooth because this is flat, so this is a smooth flat section. So we get non-vanishing flat section at the origin. This is an interesting thing because this shows up in the final result. So essentially, this is the key point of the computation, that you have non-vanishing flat sections at the origin. Okay? This gives me as an answer the following, that first the quantization is going to live in H1, okay? And then in the quantization, first you're going to fish all the regular Boltzmann leaves. These contribute C, each one. And then when you have an hyperbolic singularity, what is this thing? You have a collection that corresponds to the Taylor expand. So the invariants are given by 2 Taylor expands at the point. So this is in particular infinite dimensional, so not very pleasant, because if you look for the quantization of a compact manifold, you want a finite dimensional representation of space. So let's say Kostant formula is giving me some infinite dimensional contributions. From a point of view of singularity theory, from a point of view of geometric quantization, this can be disappointing. From the point of view of singularity theory, it's nice, because you see the singularities here, first thing. Second thing, you can compute this sheaf cohomology also in the semitoric case, even if you don't have still the global classification. Just with this semi-local information of the singularities, you have enough to compute globally this sheaf cohomology. So it's sort of nice still. So let's take the rigid body. Let's quantize the rigid body with the Kostant, with this formula. So if I use this recipe, then the quantization will have, in the rigid body case, of course I'm going to have these 4 elliptic 2 hyperbolic singularities, okay? So the answer is that the elliptic singularities, Mark Hamilton did this, this is the answer, in a neighborhood of this point is toric. So I don't see the singularity. The singular point doesn't contribute. If I look at, if I have this hyperbolic singularity, then it shows up as an infinite dimensional representation with this Taylor expand. And then I will have all the regular contributions. So in particular, if I take the sphere with the polarization given by the rigid body, and I take the sphere with the polarization given by the rotations on the sphere, then of course the polarization, I have a case in which this geometric quantization depends strongly on the polarization. Okay? Oh my God. What's going on? Okay. Il y a trop de lumière. On ne peut pas voir le dessin fantastique. C'est pas moi, c'est pas moi qui l'a fait, c'est Marsden. Okay. Okay. So, well, thank you. This is not such a nice picture. Well, I mean, this picture is, yeah. Okay. If you've seen this picture before, if you go to the library, the book of Marsden, he has this picture in color. What happened is that we wrote to him when we were writing this paper with Mark, and he gave us this version in gray, so we could use it. So it's a picture done by Marsden, or maybe a student of Marsden, I don't know. Okay, so So the conclusion is that it depends strongly on the polarization, because if I look at the toric picture, where the polarization is just the sphere, okay, then what I'm gonna have here, the only contributions may come from the singularities, but they count 0. Okay, so it depends strongly on the polarization I consider. Okay, let's go far. I'm at the end of my talk. I think I have still 5 minutes, right? Yeah. This is a good moment to start doing symplectic cutting. So I'm gonna show for you, I did already the toric case. I did the hyperbolic case. What about the semitoric case? Let me start with an example. I'm going to construct for you K3, okay? I think it's a good moment now, 5 minutes before the end of my talk, to construct a K3. I'm going to do it starting from CP2, which we saw it's a toric manifold. We even showed what was the action at the beginning of my talk from the Delzant theorem. And I'm going to start doing these things that people working in Delzant theory do, which is I start doing blow-ups, okay? So I blow up CP2 at 3 points, and I still get a toric manifold, okay? This toric manifold. Of course, you say, well, you're showing me the polytope, but the Delzant theorem is telling me that the polytope gives me one-to-one correspondence with the toric manifold. So whatever I inflict on this poor polytope is going to go back on the manifold. Okay? What about if I do symplectic blow-up again? This corresponds to cutting out this vertex. So I get this picture. Wait, this is toric. So how are you gonna do the K3, which you told me it was semi-toric? Wait. I'm going to do one thing. I have these singular points here, which are totally toric, okay? And what I'm going to do is I'm going to push them inside the polytope. This push inside the polytope, which sounds a little bit cruel, is indeed something that was studied by Margaret Symington. It's called nodal trading. What it does is to produce for you, is to convert toric singularities into semi-toric singularities, so into focus-focus singularities. Okay, so after I do here we have a toric manifold. Once I do the nodal trading, this is no longer toric, it's semi-toric. Okay, so now what is this manifold? I have here exactly 12 points. Okay, I have these 2 parts, and what I'm gonna do, I'm going to construct K3 by gluing 2 of these manifolds, which I do a Gomf sum. Sorry, this is T2. I didn't go over, this is a 2. An error here. So I glue along, the boundary of this is going to be a torus, and I just do the Gomf connected sum of these 2 of them, okay? And this is going to give me a K3 surface. And this K3 surface, so when I glue, so I go back, I have just 1 minute, but this is quite cute. So I start with CP2, I blow up at 3 points, then I blow up again, I have a toric manifold, I push the singularities inside, I get focus-focus singularities, and now I glue. So I get a K3 surface. Okay? Now I'm going to compute the shift cohomology computation of this K3 and compare it to the Keller case. Of course, I can do this with, I mean, if I'm interested in mathematical physics, I can look at, for instance, at the spin-spin system. That's quite nice. I can also look at a spin-spin system as a nodal trait of the square case. So square is totally toric, and I just push inside one of the points. This gives me the spin-spin system, which has these first integrals. I can do games with the spherical pendulum. I don't know, Romero Soya, who's my student, likes a lot to play with these games. So I do the K3, but of course I have a list of examples where this works, and it's semi-toric. All of these are semi-toric. For instance, the couple classical spin and harmonic oscillator, which has this equation, is also an example of semi-toric system. So what is the computation? Okay, I did a computation already, and I think in a talk we only have to have one tedious computation, so I did my tedious computation before. Now we are going to believe this result. By the same kind of tedious computation I did in the regular case, I get a little bit more complicated, because I have a focus-focus singularity. Okay, and it turns out something very interesting, that whenever I have a focus-focus singularity, and we are going to see this on Wednesday in the talk of Sue Tolman, I have an S1 action, which I can use. I don't have a T2 action, but in the neighborhood of this point, I have this S1 action, and I use this to prove part of the, so how do I compute this? I compute this with my Herbiatories and Cunard formula. And a key point of the computation is that in a neighborhood of a point, the cohomology vanishes, and for this I need to use the S1 action that I have here, this S1 action that I have in the neighborhood of a torus singularity. So let me look at the answer. The answer is that I have some regular Bore-Sommerfeld leaves that survive, and then I have some contributions. What is this? This is the sum, okay, of Bore-Sommerfeld leaves that are a focus-focus Bore-Sommerfeld leaf, and because I may have different pinches, NP is the number of pinches I may have. For each pinch, I have an infinite dimensional contribution. Okay, so the answer, also in the semitoric case, is that the sheaf cohomology computation of Kostant still gives me infinite dimensional, even if we initially conjectured that it, in the semitoric case, was going to be finite dimensional. A bit disappointing, though, that it's infinite dimensional. I mean, could you just take this out and get a finite dimensional thing? Still, just for you, I'm going to do the computation. So in the K3, I take this formula, and in the K3, if I assume that the points here that come after the nodal trait, all of them, which are 24 of them, are Bore-Sommerfeld, because some of them may fail to be Bore-Sommerfeld, then the quantization of K3 looks like this. It has a finite part, which has a 14, and it has this infinite part. Then you look at this equation and say, what about if you quotient out this infinite part? Can you make some sense of this 14? Okay, let me compute for you in my last slide what is the Kähler geometric quantization of this guy. Well, the Kähler geometric quantization is just the computation of H0, but we can compute H0 just using the first Chern class of the line bundle. And you can compute the first Chern class of the line bundle because you have this integral formula. Essentially, you just need to understand the volume of the K3. It's so good that we have this K3 presented as a Gumpf sum along the torus, okay? Because then we know that this integral is additive. So we just need to add up the volume of these two toric manifolds. Very good, because it's toric, we know how to compute the volume, okay? We just need to count. Well, we have 100 formulas relating the volume with the number of integral points inside. So the answer, if you do the computation, the Kähler computation, in which you just need to compute H0 of the, so you just need to compute holomorphic sections, okay? Then you get finite answer, but you get 50 here. So still a mystery. What about this 40? What if you are able to quotient out somehow this infinite thing? Still you don't get the same answer. So, well, I don't know. That's the end of my talk. So I just wanted to go back to the Kähler case and show how it connects. Thank you.
Thank you.
Hi, Eva.
Hi.
So first, refer to you mentioned several times that when you do metaplectic correction, you get the same answer. And again, exactly what you mean by metaplectic correction might be subject to a different private discussion.
Yeah.
But I just want to mention the recent paper of Jennifer Vaughan, where she does do...
Sorry?
Jennifer Vaughan.
Okay.
So I guess she works with the so-called MPC version of metaplectic correction, but at least in the case where you have a metaplectic correction, should give you the same answer. And she does computation for toric varieties, which give a different answer than the usual one.
Okay.
And which, in fact, an answer which is sort of.
But it's a spin. This is a different thing, I think.
No, I'm sorry. Well, we can talk about details later. But maybe I should be advertising this work. Where, for example, if you have in the case of a two-sphere, you have a segment. If you take Bore-Sommerfeld, including the endpoints, it would be the length of the segment plus 1. If you took interior, it would be length of the segment minus 1, and that's what Mark Hamilton has in his case. And hers would give you exactly half of the segment, namely points like this, the first one would be just distance 1/2 from an endpoint.
Okay, I don't know. Let's look at the computations.
There's a version of the definitions which actually give us sort of a more interesting answer and more interesting effect of the metaplectic corrections. I'm saying it just to advertise Jennifer Cohen's work.
Okay.
Thank you. Another question? If not, we can thank the speaker again and resume at 11:30.